Hello everyone, this is Taylor, and welcome to my walkthrough of Question 8 of the Spring 2019 exam. On any given day, Alan will play either one or two games of billiards. If he plays one game today, he'll play one game tomorrow with probability 0.6. If he plays two games today, he'll play two games tomorrow with probability 0.7. His probability of winning each game is 0.6. It is now Monday, and Alan played two games today. Calculate Alan's expected number of wins 2 days from now on Wednesday. To summarize this problem, this is a Markov process problem because you have transitions from one state to another. However, something that sticks out to me for this problem in terms of approach is that there's only two states. He plays either one game or two games. And then also in terms of long run expected values, none of that's going on here because we're just going from Monday to Wednesday, so there's only two transitions. So whenever I see problems with this few moving parts in terms of total possible combinations of states over time, I find it really helpful to just draw all possibilities out. So we're going to eventually see that in a diagram I prepared. But first, just that required knowledge. Both of these are, I actually used these properties and had required knowledge blank and had to really think, okay, what properties am I using? Because I feel like sometimes you use this using intuition instead of thinking about the actual mathematical principle, which is when you have the expected value of the product of two random variables, if those variables are independent, you can actually split that out and just take the expected value of x multiplied by the expected value of y, just because that covariance component is going to be 0. Second, the expected value of x is the probability weighted average of the variable. I have this written out twice, whether the variable is continuous or discrete. So in the case of this problem, we're going to be looking at discrete. Jumping into the calculations. So again, this, obviously you're not going to have access to image files, but for this type of problem, it's really helpful, I think, to just draw up this tree of all possibilities when there are as few possibilities being considered. So that is, you start on Monday with having played two games. And then you can either play two games or you can play one game. And that's the two possibilities for Tuesday. And then going into Wednesday, from those two states, you can transition to the two states. So there's 4 total possibilities for Wednesday. So taking these probabilities just from up top, so we know that probability of two games 2 days in a row is 0.7, and then 0.6 for when you played one game, and that carrying through to the next day, and then doing 1 minus that for those other probabilities. So 2 to 2 is 0.7, 2 to 2 is 0.7, 2 to 1 is just 1 minus that 0.7, which is how you get 0.3. Then likewise, you can come down to this one, and then there's a 60% chance you play one game on Wednesday because you played one game on Tuesday. Then, I'm not sure if it's called out explicitly, but I think just implicitly you're assuming from one day to another not independence, but just those conditional probabilities. So we're just going to carry this through. So we're taking this 0.3 multiplied by this 0.6 to get 18%. So there's an 18% chance that our person here is going to play one game on Tuesday and then one game on Wednesday. But that's not the only way that he can end up playing one game on Wednesday, because if you recall, this question is only interested in what ends up happening on Wednesday. He can also play 2 games on Tuesday and then transition to one game on Wednesday, and that has a 21% chance of occurring, again just by multiplying these two probabilities. You can do the same thing for the other branches, and that's how I get these red numbers, which are the probability that you end up playing 2 games on Wednesday. So all of this work for this diagram gets you these two numbers. So there's a 61% chance that he ends up playing 2 games, and a 39% chance that he ends up playing only one game. So now, in terms of the actual kind of final calculation, where we bring everything together, which is, what do we care about? We care about the expected number of wins on Wednesday. So how many games do we expect him to win on Wednesday? Well, that's going to be whatever the win rate was multiplied by the games played. However, this is where that independence comes in, because we know that the win rate is 0.6. And this has nothing to do with how many games are played on a given day or how many games were played on the previous day. It just is 0.6. And since that is constant, we know it's independent, and that's how we can pull this out. So instead of having to deal with this product, although we could, because it is just 0.6, so it's straightforward and ends up being the same calculation, we can actually break this out and pull that win rate expectation out separately. So that's why we can break that out and then get that 0.6 here. Then separately, we want to know, well, how many games do we expect him to play on Wednesday? So that's just that probability weighted average. So 61% chance that 2 games are played, and a 39% chance that 1 game is played. And so we end up getting an expected games played of 1.61. So if we expect 1.61 games to be played, and we expect 60% of games to be won, we would expect 0.966 games to be won on Wednesday. Scrolling up, we see that falls in the range specified by C, and that is our final answer. Please be sure to like or subscribe if you find these videos helpful. Thanks.